Okay, well, thank you very much for coming back. My name is Carl Becknell. We're doing Appendix Video 2 today. I'm sorry there's been a bit of a delay in between the videos. I'm going to try and get them out a bit quicker now, but work has been very busy. My apologies right at the start. If you own an AMD processor in your computer, or you've got a PC which does not have hyperthreading, for example, a Core i5, then this will not apply to you directly, but you may find it interesting to watch anyway. The reason I've chosen to do a little session on hyperthreading is because being involved in some of the chess forums, this is a question which comes up every 3 months or so. Someone will ask, what is hyperthreading? And it gets answered, and then 3 months later somebody asks the same question again. So I thought it'd be worthwhile to do a session on this. Let's start at the beginning. What is hyperthreading? In the old days, you had a CPU inside your PC, and it was very simple. You had one PC and one CPU inside of it. Newer processors have these things called cores. They're a little bit like processors in their own right, like mini CPUs within the main CPU. So, for example, it's very common to have a quad-core processor with 4 cores inside the CPU. And those cores are physical cores. If your tiny little hands were small enough, you could open up the top and touch them. It is a physical thing. Let's just move that over there. So, why did hyperthreading come about? One of the challenges that programmers face is how to write code in such a way that the CPU is kept busy in a worthwhile way. If one core is running one program on Windows, quite often it won't be busy all of the time. And what hyperthreading does is, instead of each core generating one virtual core, it generates 2. Now, these cores are not physical. You can't physically touch them. They're virtual cores that have been generated off the back of each physical core. 2 virtual cores per physical core. And Windows will interact with both of them, sending different threads or little programs, if you like, to each virtual core. I'm not sure how good this illustration is, but maybe it will help. If you imagine quite an intelligent person doing the washing up around the house and the kitchen, their brain is not going to be occupied all of the time. But if you ask them to do the washing up and the crossword at the same time, and you got them to do 2 tasks at once, there is a higher chance that their brain would be busy all of the time. And really, this is Intel's way of trying to squeeze more performance out of the system. By generating 2 virtual cores, by having hyperthreading, it enables Windows to stand a better chance of keeping each core busier more of the time. That's the basic premise behind it, I believe. Now, the big question is it worth it for chess? And we're going to tackle this question in 2 parts. First of all, hyperthreading in infinite analysis. And second of all, hyperthreading in IDeA. Now, please can I ask you, if you've not yet seen Appendix Video 1, you really should see that one first, because in Appendix Video 1 I go into some detail about why adding more cores to an engine reduces the search efficiency if you're using it for infinite analysis, where you have all of your cores running one single engine between them, and all of your cores are trying to make that engine go as fast as possible. Of course, a 4-core system is going to be faster than a dual-core system, but it won't be twice as fast. That's the point. And in that video, Appendix Video 1, I explain in some detail as to why that is the case. And it's because we introduce search inefficiency as we add more cores to the engine. Right, first of all then, hyperthreading with infinite analysis. When would you do such a thing? Well, of course, you would do it when we're in Sandbox. And there's an example of Houdini 3 running in Sandbox. And what I decided to do was a little experiment. I decided to try a couple of different engines and to see what the results were when I switched hyperthreading on and then hyperthreading off. And the two engines I chose were Zappa Mexico 2. It's an old engine now, it's about 5 years old. But I chose it because when it came out sort of about 5 years ago, everyone raved at how well it did on big hardware. So I thought it'd be fun to test that. And I've also got a much more modern engine, the latest official build of Stockfish, which is Stockfish 5. So here we go, here's my little experiment. First of all, I've got hyperthreading off, and then after that I've got hyperthreading on. I actually filmed this in a different user interface. The user interface makes absolutely no difference, by the way, to the speed of the engine. It's not really doing much, it's the engine we're interested in. And here I've got Zappa Mexico 2. It's running on a 16-core dual Xeon system. That means it's got 16 physical cores. I'm just going to set it going now. Okay, off it goes. I'll leave it running for about a minute. For the sake of the video, I'm going to speed this bit up so that you don't have to sit here for a minute just watching it. There we go, so we're up to 52 seconds now. And hopefully I'll get some usable numbers at the bottom somewhere. There we have it. It's done 503 meganodes in 59 seconds, which is pretty good. Right, what I'm going to do now is I'm just going to shut down and I'm going to reboot the system, and I'm going to switch hyperthreading on in the BIOS. It's the only place you can usually do it. And then I'm going to reboot my system with hyperthreading on, and we should have twice as many cores to play with. So excuse me a moment. Okay, I'm back. It's the same computer. I've still got 16 physical cores, but because I've switched hyperthreading on, I've now got 32 cores to play with, as you can see there on the screen. And I'm going to let Zappa Mexico 2 have a go again. So it's thinking. We'll let it run for about a minute or so. I'll just speed this part of the video up. Okay, so we're up to 50 seconds. What do you think? Do you think it's faster with 32 cores? I think it is a little bit. Just a little bit. Hopefully we'll get some numbers we can use in a moment. Just let it go there. Okay, there we go. So it's done 730 meganodes in 1 minute 20. Now let's try and tabulate these results and see what we get. Okay, so Zappa Mexico 2 with hyperthreading off, so it was running on 16 cores, managed to do 503 meganodes in 59 seconds, which means that its average search speed is 8.5 million nodes per second. Zappa Mexico 2 at the bottom with hyperthreading on, that's 32 cores, did 730 meganodes in 80 seconds. That's an average search speed of 9.1 million nodes per second. It's faster, but the question is it fast enough? Well, that works out to be an improvement of 7%. And I can tell you now that that is nowhere near fast enough. This week I've been speaking to some experts. I spoke to, on the forums, I spoke to Bob Hyatt in America, and a while ago I've seen something posted by Robert Houdart, the author of Houdini, and this is what I've gleaned from these interactions with them. Basically, they were saying that for a doubling of cores, you'll need anywhere between 20 and 30% increase in nodes per second just to break even. The point is that as you increase the number of cores, the search efficiency goes down for reasons I explained in Appendix Video 1. So to keep the same speed, you're going to need to increase the number of nodes per second just to break even by anywhere between 20 and 30%. And as you just saw, Zapper Mexico 2 increased its speed by 7% with hyperthreading on, which is nowhere near fast enough. So just to make this really plain, with hyperthreading on, Zapper Mexico 2 was going slower. If you want to speed up the engine, you need to switch hyperthreading off. Now, I tried this again with Stockfish 5, and these were the results I got. With hyperthreading off, it did 958 meganodes in 56 seconds, giving 17.1 million positions per second. With hyperthreading on, that's 32 cores, it got a search speed of 20.9 meganodes per second, which works out at 22% increase. Now that's an interesting improvement because it's just in that bracket that we talked about. My hunch is it's probably too low to make it worthwhile, but it is interesting. If there's any experts watching, I have a question for you, and it's this. Is it that Zapper Mexico is a well-written engine and keeps the CPU busy with hyperthreading off, and therefore when you switch on hyperthreading it gains very little? Or is it that Stockfish is actually the better written engine and exploits hyperthreading somehow better than Zapper did? My hunch is that Stockfish is probably better written than Zapper just because it's newer and it's got lots of people contributing to it. But I'd be quite interested to know the answer to that question. But if you're an average user listening to this, basically it doesn't really matter. What you need to know is that if you switch on hyperthreading, you are probably, almost certainly, slowing your engine down. It is not worth it. Even in the case of Stockfish, 22% gain in nodes per second is not going to be enough to make it worth your while switching on hyperthreading. So that is that, I'm afraid. The other thing to bear in mind is that when I did this experiment, I noticed certain things happening when I did it. When hyperthreading was switched on, I plugged my workstation into a power meter and it clearly was using more electricity with hyperthreading on. More electricity means more heat is being produced and a lot more noise was being produced because the fans were having to work that much harder to cool the system down. It actually sounded like a jet engine when hyperthreading was on. I'm not saying your system will crash with hyperthreading, but you're more likely to have a crash if the system is hotter, particularly if you live in a warm climate or your room is not very well ventilated. And certainly I noticed that with the system under full load, with hyperthreading on, it was less responsive than the system under full load with hyperthreading off. And that might be because each core is maxed out and it's got nothing left to give. I mean, even moving the mouse around the screen was tricky. With hyperthreading turned off, you get the opposite of that. So you'll be using less electricity, which means it'll be quieter and cooler. Probably it'll be more stable, and the system was certainly, in my case, more responsive. So in conclusion, I'm saying to you, it's nearly always a good idea to switch off hyperthreading in the BIOS. But the big question is, does all of that hold true when we move away from infinite analysis and into the realm of IDeA, which is what these videos are all about? Now remember what we're doing in IDeA. In IDeA, we are running one instance of an engine on each core. So for example, if you've got an 8-core system, you would be running 8 versions of, let's say, Komodo on each core, with each engine running on a single thread only. There is absolutely no parallel search taking place with IDeA in the classical sense that we talked about just now. And that makes things really interesting, because the big problem with hyperthreading, or sorry, one of the big problems with hyperthreading with infinite analysis is that we are introducing search inefficiency. But by getting rid of parallel search, we remove that, and therefore the experiment becomes interesting again. So let's have a go. Remember, IDeA looks like this. I'm just going to set this going. There we go. You've got 8 instances there in the green of Komodo 7 running, and we're doing it in IDeA, as I've highlighted in the bottom left. And very importantly is this little bit here, where I'm pretty sure this didn't exist in earlier versions of IDeA, but what we've got now is a way of telling how fast each core is running. And if you do experiments for yourself, where you're switching hyperthreading on, hyperthreading off, you want to be making sure that each engine running on each core is running at approximately the same speed. They'll never run at exactly the same speed because they're analysing different positions, but if you notice, for example, that one engine is running at 1/10 of the speed of another, you've got a problem. And you need to be very, very careful if you do experiments with hyperthreading that all of your engines are running at approximately the same speed. And that's what I did. I did this twice with hyperthreading on and hyperthreading off, and I compared the results, and this is what I got. I'll explain it to you in way of a fictitious example, but it'll make the point, I hope. Take a typical quad-core processor which has the hyperthreading ability. Something like a Core i7 will do it. That processor obviously has 4 physical cores. Let's say, purely for the sake of argument, that if you're running an engine, let's say, for example, Komodo, on each core, it will be searching at 1,000 kilonodes per second. It'll probably be higher than that in real life, but just for the sake of making the maths easy, let's say it does that. That means your total processing power is 4,000 kilonodes per second, because each core is running at 1,000 and you've got 4 of them. There's no search inefficiency taking place, so it is as simple as saying you are running at 4,000 kilonodes per second in total. Now let's do the same experiment, but with hyperthreading on, and this is what I found. With hyperthreading on, we've still got the same processor, it's still got 4 physical cores, but because we're using hyperthreading, we're actually dealing with 8 virtual cores. And what I discovered was that each virtual core was running between 60 and 65% of the speed of the physical core. So between 0.6 and 0.65. Let's call it 0.6 to make it safer, more conservative. That means each core is running at 600 kilonodes per second, which is slower than it was before, but you've now got 8 of them, which means that your total processing power has actually gone up to 4,800 kilonodes per second. That's a 20% gain in performance. That's pretty good. Right, let's try and draw things together then. What are we actually saying here? In summary, I would recommend to you to turn hyperthreading off for all of your uses. And if you are a beginner watching this video and you're a bit confused, I would just say to turn hyperthreading off full stop, even if you're using IDeA. But if you're the sort of person who likes to squeeze out every last bit of performance you can from your system, and you're using your computer solely for IDeA analysis, and you're not chopping and changing and going in between infinite analysis on Fritz or something, or in Sandbox or whatever, but if you want a dedicated system where you're just using your PC for IDeA and you don't want to have to faff around with engine settings to compensate for switching hyperthreading on and off, then what I would recommend to you is you at least have an experiment with hyperthreading and just see what happens. And if you are using it for exclusive IDEA use, then you do potentially gain 20% performance improvement. But be careful with your computer, be careful you don't wreck anything by changing settings in the BIOS that you don't really understand what you're doing, or you don't know how to change back again. And if you do decide to switch hyperthreading on, then just bear in mind you may be a bit more susceptible to crashes and so on. I hope that helps. Thanks for watching. Next time we won't be doing another appendix video. We're going to be going back onto the main videos, and we'll be looking at which engines to use in your IDeA projects, and also what settings to use as well. Thank you for watching.